Okay, let's dive right into this explainer and look at the actual blueprints behind the complex silicon chips powering our everyday devices. When we think of computing, we almost always jump straight to software, right? Lines of code executing on a processor. But we have to ask, what language writes the processor itself? Today, we're exploring SystemVerilog. This is the foundational language that lets engineers design and, honestly, just as importantly, test the microscopically complex digital circuits that make our modern technology possible. Here's our agenda for today. We're going to cover 1. The limits of Verilog, 2. The birth of SystemVerilog, 3. Core design fundamentals, 4. Sequential and combinational logic, 5. The power of verification, and 6. SystemVerilog today. Let's get right into it. Section 1. The limits of Verilog, from its 1980s origins to the 90s complexity crisis. Now, you really can't appreciate a solution until you understand the sheer scale of the problem it was trying to fix. So back in the mid-1980s, Phil Morby over at Gateway Design Automation created Verilog. And at the time, it was a massive leap forward for modeling digital circuits. Fast forward to 1995 and it gets standardized as IEEE 1364. But as we all know, technology moves incredibly fast. By the late 90s, Moore's law was just pushing chip complexity to staggering new heights, and designs simply outgrew the original Verilog language. Engineers were hitting a real crisis. They didn't have the abstraction needed for these massive environments, and testing these sprawling chips to make sure they'd actually work was becoming, well, nearly impossible. Section 2. The birth of SystemVerilog, the solution to the chip crisis. Engineers desperately needed better abstraction and some seriously advanced verification to stop these chips from failing before they ever hit the manufacturing floor. A simple design tool just wasn't going to cut it anymore. So around 2002, Synopsys steps in and introduces this superhero upgrade, SystemVerilog. See, traditional Verilog was strictly for registered transfer level, or RTL design. It had weak data typing, which was a nightmare for bugs, and it completely lacked features for large-scale verification. SystemVerilog absolutely changed the game by combining hardware design features with advanced, object-oriented programming constructs specifically built for testing. It wasn't just about building the chip anymore. It was about rigorously proving that the thing actually worked. So, with the stakes of modern chip design firmly established, we really have to ask, what do these new fundamentals actually look like? How does an engineer use code to describe physical electrical paths? Section 3. Core Design Fundamentals. Building the blueprints. Let's break down how this language constructs physical hardware step by step. Think of it like a giant puzzle. Just like a building has rooms, a SystemVerilog design is built using modules. A module is basically the absolute fundamental structure in the language, representing a specific, distinct block of hardware. You can picture it as a black box with inputs and outputs. Inside that box, you define the behavior, whether that happens to be a simple logic gate or a hugely complex memory controller. Then you wire these modules together to build an entire system on chip. But to make those modules work flawlessly, SystemVerilog had to fix the very foundation of the data itself. It introduced strong typing to solve Verilog's notoriously weak typing issues. In the old days, engineers were constantly tripping over, actually, scratch that. They were pulling their hair out over when to use the reg type versus the wire type to connect elements. SystemVerilog beautifully simplified the whole shebang by introducing the logic data type. This one simple change gave us significantly cleaner syntax and dramatically fewer bugs during the design phase, saving engineers literally countless hours of debugging simulated shorts. Section 4. Sequential and combinational logic. Bringing the hardware to life. Okay, let's look at how the language handles the actual logic flow within the chip, how data moves, how it changes, and how it stores itself. SystemVerilog organizes behavior using specific always blocks. The first major one is the always_com block. This is specifically designed to handle combinational logic securely. And combinational logic just means the output depends entirely on the current input right at that exact moment. It's like a math equation. By using always_com, the software instantly knows your intent, which prevents accidental memory loops from forming in the silicon. Next up, we have the always FF block, and this one is uniquely dedicated to sequential logic operations. The FF here stands for flip-flop. Now, unlike combinational logic, sequential logic relies on a clock signal. It holds onto data. It has memory. This specific block guarantees that the hardware you synthesize will trigger exactly on a clock edge, which is essentially the heartbeat of any modern digital circuit. And finally, the always latch block rounds out our specialized logic handlers. Latches are a very specific type of memory that are level sensitive rather than edge sensitive. While they aren't used quite as frequently in modern synchronous designs, having a dedicated block for them is crucial. It means engineers can safely implement latch-based designs without the software accidentally confusing them for standard flip-flops, which, by the way, is a classic cause of really nasty hardware bugs.
Now, this right here is where the magic really happens, especially for those of you coming from a traditional software background. While if and case statements look exactly like standard software coding, in SystemVerilog, they dictate physical hardware behavior. Think about that for a second. When a C++ program reads an if statement, it executes sequential instructions. But when SystemVerilog reads an if statement, it synthesizes physical hardware paths, like actual multiplexers, right into the silicon blueprint. You are literally writing circuits with code. No way around it. That's pretty amazing.
Section 5. The power of verification, inspecting the virtual city. So, designing the chip is only half the battle. Remember the famous 1994 Intel Pentium bug that cost them nearly $500 million? Yeah, ensuring a chip actually works before it goes to manufacturing is absolutely critical. And this is where SystemVerilog truly shines. It brought a whole suite of superpowers to verification. It brought object-oriented programming to hardware testing, letting engineers build these massive reusable test environments. It features built-in randomization to automatically throw thousands of random constraints at a design just to try and break it. It uses assertions to continuously monitor the design and flag if any rules are violated. It provides interfaces to cleanly bundle connections together. And it uses functional coverage to actually measure, mathematically, if your tests have hit every possible scenario. Because of those incredibly powerful features, SystemVerilog serves as the absolute backbone of modern engineering. It is the foundational language for the Universal Verification Methodology, or UVM. UVM is the industry standard framework supported by all the major electronic design automation tools out there. If you're verifying a complex chip today, you are almost certainly using an environment built on SystemVerilog's. Section 6. SystemVerilog Today, the industry standard. We've seen where it came from and how it works, but how ubiquitous is it really? Well, following its initial introduction to solve that 90s complexity crisis, the industry fully embraced it. It was officially standardized as IEEE 1800 in 2005. Over the years, it has rapidly evolved to meet new demands, seeing major revisions in 2009 and 2012. And the 2017 revision, that's what you'll find being widely used across the industry right now. It is the absolute bedrock standard that hardware engineers rely on every single day. The impact here literally cannot be overstated. Think about it. The device you're using right now to watch this explainer is powered by a high-performance CPU, a GPU, or some complex system on chip. Whether it's the processor in your smartphone, an application-specific integrated circuit in a massive server farm, or an FPGA powering telecommunications, it was almost certainly designed and rigorously tested using SystemVerilog. It is, for sure, the dominant language shaping our digital world. SystemVerilog evolved from Verilog and completely saved the hardware industry in the early 2000s by unifying design and testing into one powerful language. But as Moore's law pushes chips even further into the microscopic realm, packing billions of transistors into spaces the size of a fingernail, we're left with a massive question. As these digital systems grow even more unfathomably complex, what will the next evolution of hardware description require to keep pace? What new verification superpowers will we need next to ensure the systems of tomorrow don't just collapse under their own complexity? Let me know what you think.